before. Isn't it really convenient? We're seeing it almost exactly the same again. But today we are going to be looking at parallel RL circuit. So the resistor and the inductor are going to be in parallel with each other. Last time we looked at the series equation. So XL, that doesn't necessarily correspond to series, but right, that's what we have. We're still going to be able to use that definition. So 2 pi FL. For series impedance, it's going to be R plus JXL. So it is a positive imaginary component because we have it's leading in the inductor. And then we can still go through and use trig to figure out the go from the rectangular to polar or polar to rectangular, depending on what we have. Any questions from last time? Today we're going to go through and we are going to be looking at the parallel version and kind of seeing what that looks like. Sorry. So we'll be seeing what that looks like and going through and doing that. So we'll look at the impedance and admittance of parallel RL circuits, talk about analyzing them, and then we will go through and talk about how to do series parallel combination circuits. So with the like kind of similar to what we had for the parallel RC circuit, the equation is going to look a little bit different for the impedance. So this is it's like going through and doing its calculation. It is very rarely that we would go through and actually use it this way. So we can go through and do some simplification down with that, which gets it to, or I guess this isn't simplified. This is going through and writing it out kind of completely in the polar form. So pulling out the angle parts again, or the first term here, that is how we would go through and use it. But with the second term, so the angle term there, instead of having to do sine minus the inverse tangent part, right, we can just flip over the tangent. So this is typically how we will see the equation and how we would go through and use it for parallel RL circuits. So this should look fairly familiar in comparison to the parallel RC circuit. So for the parallel RC circuit, it looked exactly the same except for the L's were replaced with C's. So that would mean that right, X is still in the same location except for, so it's XL for the inductor. So resistor inductor case, it's XC for the resistor capacitor case. So the forms look the same again. This is another reason we've been going through and using these X values. So by having the right, the reactance in terms of X, it allows us to see a lot of symmetry in between the equations. Questions on the impedance of an RL circuit? Yes.
We're going to be doing all three of them together.
Next week? Yep, or did the RLC circuit next week. So we'll have nothing changes with the resistor part. It's the imaginary part that undergoes the change, and that's it.
We'll be doing like examples.
Yep. Yeah, well, we're gonna have to go through and set it up so we know how to go through and do the impedance for them in series and in parallel. Then we can go through and basically you can revisit everything we did with resistors, we can do with impedance values as well. So superposition, loop method, mesh method, all those fun stuff. Any other questions? So as with the RC circuit, sometimes it might be easier to go through and deal with the inverses. So with that here, we have the same exact equation for conductance. It is still just the inverse of the resistance value. Now we have a slightly different version of, right, so for a capacitor, we had our BC value, that was our capacitive uh, susceptance. Would you know it? We have the inductive version as well. Thank you. So here we have BL. It's going to be 1 over XL plus or minus theta. Again, same equation that we had for our BC. Here, the theta value is a little more generalized. If we look at the capacitor equation, that was always, it was XC angle was minus 90 degrees. Here, it's a little bit more generalized to be plus or minus with going through and seeing that. That is typically how you see the BC and BL values represented. So that's how you'll see them moving forward. Yes. Oh, no, it's supposed to be X. Oh, sorry. Yeah. Yeah, sorry. This should be. Yes. I copied an equation because I didn't want to have to copy the format and I made a mistake there. I thought I had fixed it. Thank you. So, yeah, so it's BC with the angle, or again, you can have that imaginary part. Yeah, but again, this is the more generalized form. We can also have the admittance. So this is going through, and when we have them, so here we have our B and the BL in parallel. Because they're already inverse, we would just be able to go through and add them together. I also double have a negative here. So that's cool. Just double check. Pretty sure I just have an extra negative. But right now it's the inverse of the Y value. So depending, again, you don't have to go through and use these. They're 100% optional. It just might make your math easier to go through and solve. When you have simpler terms, it may be easier to just go through and keep it in terms of the singular one that we have. Yes.
Why is conductance?
So if we look at how we utilize that vertical plane being imaginary, or the horizontal is real, vertical is imaginary. So it's along the real part, so it has there's no portion of it in the imaginary section. So yeah, it's just with the theta value for the for BL, here's not necessarily going to be 90 degrees because we have that resistor in there. So that's why this one isn't the hard 90 degrees with it. But it will purely be imaginary at the end of the day. So with the ones we're dealing with in this class, we could probably just call this plus 90. It's more generalized to have, it's just the more general form to have it with the theta value be the plus or minus or the minus plus. Just a more general representation that you see in other textbooks as well. So for BL, it's totally okay to just, for the ones we'll deal with in class, this will be true. And then for admittance, you would have to go through and figure that out. Any other questions? Because when you flip it over, you're looking at the negative of it. You flip your angle goes, because you're flipping, instead of being down here, you're up here. The negative theta. For that, because you're going around clockwise versus counterclockwise. Any other questions? Let's go through here and let's look at 21 and think about how can we find the impedance in rectangular form for this circuit here. So before you go through and solve, just knowing what we're eventually going to go through and do here, we are looking for Z in its rectangular form. So we're going to have some real plus some imaginary component for it. And in order to go through and do this, we are going to follow similar steps for what we did with the parallel RC circuit. And so with it, we are going to have to go through and find XL to go through and utilize. So just looking at calculating XL here, right? It's 2 pi frequency times the inductance value. Will I need to convert in this case? End of the day, my XL needs to be in ohms, so I probably should in this case. So my frequency is given in kilohertz and my inductance is given in. No, in that case, that's 100% optional for this one. But I do need to convert my frequency and my inductance into SI units in this case because they will not cancel out. So once you do that, go through and try to solve for the rectangular components. In this case, that does not matter. It would matter if we wanted to go through and then find the voltage across the different components, which we're not doing in this case. Have we done it in class? It was not something like this, though. Yeah. So we don't always necessarily need the angle to go through. Yeah. Just like we don't always necessarily need the voltage, but the textbook's trying to get you familiar with the notation of having the voltage, the angle, and the frequency. Yeah. Anybody want more time solving 21? So how did you guys go through and solve for the impedance value? Did you guys use Z directly or did you go through and use GBL? Yeah, let's see. So we can go through and we can use Z is equal to R XL over the square root of R squared plus XL squared to find the magnitude for it. When I solved for my XL value here, you may have noticed I left it as 3.2 pi. This is because I don't want to drag around the decimal points for going through and plugging that in. That is fine for when you're doing the work, but at the end it should not have pi in your answer. It's going to start at a polar and then we're going to convert it into rectangular. We don't have a direct way to just write out that value at this time. So for R here, that was given as 12 ohms. I'm going to drop all my units for the sake of space. I'll have 3.2 pi over the square root of 12 squared plus 3.2 pi squared. Taking that and plugging it in, I got that for the magnitude of Z. I have 7.70621, and that is going to pop out in ohms. For finding the angle portion, it's the inverse tangent of the resistance over XL. Something that I know I personally am very guilty of is sometimes when I write XL, it looks like XC. I'm not super concerned about it when we're doing a very clearly RC or RL circuit. But when we go through to look at RLC circuits, you will want to somehow make sure that your L's look like L's and your C's look like C's. So I am okay if for your XL, you use a lowercase cursive L instead. I find that that is probably the easiest way to go through and identify them, especially if you have rushed handwriting that gets a little bit messy. I'm going to have inverse tangent of 12 over 3.2 pi. Taking that and plugging it in, I got 50.045 degrees. So this is my polar form. How do I go from polar into rectangular? Mm-hmm. Yep, back to using more trig, places you didn't think trig would be important. So here, right, we'd just go through and add these. So we'll have 7.70621 ohms, cosine 50.045 degrees. For the imaginary part, same thing, but sine, and I also have the J here to remind us we can't just add these values together. So for the real component, I got 4.9488 ohms. And for my imaginary, 5.9072 ohms. Oops, forgot my J there. So going through and writing this out and rounding it to 3 sig figs, I'm going to find that my impedance in rectangular form is going to be 4.95 plus J5.91, and that is all measured in ohms. You can put the ohm symbol behind the individual numbers. You could also just parentheses and put ohms on the outside. I do not care which way you do it, as long as you include your units. Yeah. I'm okay with that, as long as it's there. I'm just trying to match the notation of the textbook to the best of my abilities. I'm sure you will notice that, or I guess you won't notice because I'll delete it. But when I type a lot of the solutions, I'll put I at the end, and then I'm like, this textbook uses J. It puts it at the front, and I'll sit there and all. It is annoying, but yeah, as long as it's there, I'm fine. Any questions on 21? So let's go through them and let's briefly go over some relationships that we can get utilizing right, the parallel situation. So if we think about uh, what's the same across them, they have the same voltage value, but that means that they can have different currents passing through them. It's going to depend on their values here. So here we have Kirchhoff's current law written out. So we have the total current that's coming from our source. It splits between the resistor and the inductor, and it can be described as the current through the resistor minus the imaginary component from the inductor. So it is different if we go through and look at the capacitor, how those signs behave is going to be different for them. Again, capacitors tend to lag, inductors tend to lead. They are opposite of each other. So we can represent this in polar form as well. So that's our rectangular form. We can have the polar form. This is something that starts to get more necessary as you would go through and try to find the current or the voltage through particular different components. So in the case of series, we're looking at the change in voltage as we go across our components. While we're in parallel, we look at the different currents inside of them because, again, they should have the same voltage across them. Kirchhoff's voltage law still applies, but it's the current that's going to be different between those paths. And here we have our phasor diagram for it. So this longer line here, this is our voltage value. And we can see that we have voltage for the source, resistor, and inductor all along the same line. As we go around any closed loop, the change in voltage has to be equal to 0. So that is why they're all in the same location. Our currents, though, do not have to be the same. So here we have in the pinkish color, we have along our real axis, we have the resistor value, and in the negative imaginary direction, we have the inductor current. So the current through the inductor, according to this and with the equation, lags the voltage in the resistor current by 90 degrees. That is why it is negative. No, because if we look at the length of it, it has a shorter length than the total part. The total current. So the length of this phasor here
Well, I mean,
is,
with the equation, I'm just confused.
this is not necessarily a subtracted value. This is an it is the I lagging, that it's showing that it's lagging for 90 degrees. But The risk, depending on how the current is flowing from the inductor, you could technically actually have a larger current through the resistor than from the source. But it's heavily dependent on where in the cycle and how strong is that induced current value. Typically, that will not be the case, but it is physically possible if you set it up exactly right.
Technically, it's a specific time where
Yes, it's a very brief incident. The inductor current will never be greater than the source. Yeah, it'll always be smaller. Because we resist the change, so it's always going to have something trying to counteract that changing AC source. And so it's always going to point in the opposite direction. That'll make it smaller overall.
theoretically, there are situations where technically it could per moment be greater because it's so far behind the current that at that moment it would be higher where, because we're talking in a AC environment, it could be where, let's say we're at 0 at that time.
Yeah, I guess if we're at 0, yes, it'd have to be
Is
greater.
there
but-
any interesting interactions that happen in those scenarios, or does it kind of dog it?
At the end of the day, it all just kind of fiddles out to be nothing exciting. Because you'll also have instances where you don't have any current that is induced from the inductor, and that's happening twice as often or at the same rate you're having the zeros happen, or the zero from the source happening. So it ends up not really being anything of interest. I'm sure you can create something where like you can use that maybe as like a timer of some sort, but if you're doing that, you should just probably use your AC source in the beginning to time it.
Using a source like that for timer is just a terrible idea at the beginning.
I don't disagree. I'm just saying that like you could use it in theory to do that, but I don't. From my understanding of circuits, I don't know anybody who has made a circuit that does it based off of that little, brief fraction of a second. Any other questions so far? So we can convert from series to parallel as well. So for this here, right, this is kind of going through and using the trig information to find the real and imaginary components. So again, this part here for the resistor is real, whereas the portion for the inductor, that is the imaginary component. So it looks but at the end of the day, right, these equations, they look pretty similar to what we saw with the capacitor. And in fact, if we go through and look at the whole general process for what you would do to go from parallel to series, it looks almost identical. Right? If we think about back to the equation at the beginning of class today, it was the same equation for parallel RL circuits and RC circuits. It's just it's XL versus XC. The same thing is true when they are in series as well. Our equations for Z looked exactly the same, other than we had XL or XC. So same general procedure as before. So with going through and doing that, you can go through and use BL, YL, and G. Those are optional things you can go through and do. It all depends on what you're going to have for that particular circuit. So with this here, this is the, right, because if we go through and do our calculation for Z, right, we typically calculate this in polar. So we'll need to go through and convert into rectangular. And we will have to go back and forth between them depending on what we are going through and doing. So when we are adding impedance values, in general, do we want to be in polar or rectangular form? Yeah, so in adding and subtracting, typically we want to be in rectangular. For multiplication and division, we instead will want to typically be in polar. So multiplication symbol, division symbol, that's typically the way we'd want to go through and do it because of how we can treat interacting with those angles with each other. So again, typically with what we will see in this textbook is we will need to take all of our parallels, put them into rectangular, and you will probably need to go through and do this in individual steps. So it's still going to be beneficial, even though I know it feels a little bit silly to, box the circuit components to label it. It is beneficial to go through and do that such that you're able to keep track of what you're going through and doing for that circuit. Questions so far? So you would take the magnitude parts, you numerator divided by the denominator, and then the angle subtracted from the other one. So it's numerator angle subtract the denominator angle. Yeah. You multiply the terms and you add the angles. Yeah. Any other questions? So same general process, convert back and forth. So here we have an example. I definitely recommend, so if you go through and look at the textbook, pretty much all of section 16.6 is examples. And in fact, that's pretty much like it has like maybe two paragraphs of text. I guess 3 paragraphs of text, but it has examples and working through those. So for this one here, right, we would want to go through and similar to what we did with resistors, probably start as far away as possible. We would probably want to start with this one here. So deal with Z2. So this would be L2 and R2 in parallel with each other. So you would go through, deal with the parallel part, then combine that with these series that we have here for Z1. So you would go through, calculate them separately, then go through and combine them into a single inductance value. In the case of the second example in section 16.2, this is the circuit that you are given. So in this case, you would want to deal with the 2 in series first. So you would deal with R1 and L1. That becomes the Z1 in this case. L2 and R2, those are in series as well. So you do the 2 sets in series, then combine it into a parallel situation. So you can deal with you would have probably solve it in rectangular, go through and deal with it in polar. Questions before we do an example? Yes.
I'm wondering, so when we have a angle to our voltage source, that's just an offset to our normal angle because we could treat it whether we're with our inductor, so it'd still be our plus 90, but it would be 90 to in relation to
Yes.
this one. So it'd be 110.
Yeah, so the angle that's given with the source here is the phase angle for the source. So is it, in this case, it's starting at sine. So it's sine of 0 versus, right, because it's sine omega t plus, is it theta or phi in this textbook for phase angle? Whatever the phase angle thing is, that's the angle that's being represented here. So it's, the physics textbook is phi. Yeah, so it's just, it's saying I'm starting at sine, but if this was, like you said, 20, then that would mean that for the inductor, it's gonna be shifted by 20 as well, so it's the 110. You'll see almost every source in this portion of the textbook is gonna be 0 degrees. So we'll have a lot of 90, positive and negative 90s for that. Any other questions?
Add the rectangular forms together, right? When
Yes.
Okay.
Yeah, so you add rectangular, addition is, yeah, I guess you're never really subtracting rectangular, but yeah, you're adding rectangulars. Then with the division that you have for the parallel part. Yeah. All right, so I want you guys to look, we're gonna work through 29 here. There are two major ways I think we can go through and do this one here. So I want to talk about the two methods before we go through and decide what to do. So just looking at this here, what is your first instinct for what we should be doing? How would you simplify it?
Well, I put our resistors together and then our inductors together.
Can we put our resistors together?
Somewhat.
How?
Well, we know R1 is parallel to, sorry, R1 is in series to R2 and R3, and R2 is parallel to R3, which is in series with our inductors.
That's not simplifying, that's solving the whole question at this point. So, Matic, did you have something? Different?
I think good. From T to triangle. Right? That help.
T to delta?
Yes.
Or I guess Y technically. I don't think that is gonna help us here.
Just set C equal.
I cannot just set Z equal to these values, unfortunately.
You group it
I guess.
3 different ways.
L equal to, no,
Okay. So the two, yeah,
Is if we just forget R1 and R2 exist for a moment,
yeah,
we can just say that we have a Z1, which would be our two resistors we don't care about, and our Z2, which will be our R3 and our LT.
okay. So yeah, so the two main ways that you'll see this done in textbooks is sometimes you'll go through here and you'll combine L1 and L2 into a single inductor. And then that is going to be in series with R3. And then you have your first impedance value to go through and deal with. That is one way to go through and do it. Another way, and the way that this textbook does it, which I think is personally I find a little bit weird, is it goes through and it looks for ZL1 and ZL2. And then goes through and puts them together. And then adds, and then that's in series with the ZR3 value and goes through and does it that way. So those are the two methods that will probably work out the safest for going through and doing it. But like you said, right, we have series and parallel stuff. It's just we need to turn it into inductance first before we can go through and start combining it. So You guys want to see it where we do treat the inductors separately, or do we want to treat the inductors as a single inductor?
Same.
So that means I need to find LT here. So how do I add inductors in parallel to each other? It's inverses, so 1 over 50 millihenry plus 1 over 50 millihenry to the -1, which is 25 millihenry. I will need to then go through, and I'm just going to redraw the circuit to just make sure we understand kind of what's going on in varying levels of good art. So this is now what we have. So we have R3 here, LT, R2, R1. You don't have to draw it like this, but all right, as long as they're in the same part of the branch, I don't care. So looking at this here, I need to go through and I need to look at this section of R3 and LT. What do we want to call this? Yeah, we call this Z1. So to go through and find Z1, because they're in series, I need to find XL. Do I need to convert in this case? Yeah, we should, right? We have just hertz given. So we'll have 400 hertz and 25 times 10 to the what? It's going to be -3 henries. Taking that and plugging it in, that's going to be 62.8312. You can also figure out what it is with and leave the pi in there. It doesn't matter. This is going to pop out in ohms. So for series RL, I have the ability to write this directly as a rectangular. How would I go through and do that? Mm-hmm. Mm-hmm. Yeah. So this is what Z1 happens to look like. And I know we haven't talked about it yet. Typically it pops up in the RLC circuit for its symbol. But with inductance here, it's measured in ohms. So if you had to take a wild guess, what is the circuit symbol we use for Z inside of a circuit? I put an ohm symbol in there. If I wanted to redraw this circuit with Z1 instead of a resistor and an inductor, what symbol might I use? Yeah, it's a resistor. So we can redraw this again. It looks like this. So we'll have R1, R2, and we'll want to reference it as Z1 because we're pulling, that will be what we pull along with it. So what I want you guys to go through and do is from here, try to find the total value for the inductance.
can't, because the relationships there. So you can't combine resources. With this one. So I treat them. Yeah, it would be the inverse of. Well, this way I see carries are. I can be interested in matters again, just I visit it very term, so it gets to stay by itself. Should be fun. Yeah. Makes sense. C2 is parallel. I added them properly. Yeah, you start hanging out. Wrote stuff down, or I'll send it again. Well, the J gets put in, but nothing happens to them. That's what I mean. Yes, that's.
Any of you want more time to solve for the total value of Z? So from this bottom circuit here, how did you guys go through to start setting up to find CT?
Well, I realized that it's kind of hard to treat a C2 as R1 and R2 because the relationship of R2 has with C1. So I treated it as a C2 and 3, where Z2 is parallel to R1 and is the result of R2, and Z3 is R1.
So you called this Z3. And or sorry, Z2?
Yeah.
Yes, or did I flip your 2 and 3?
You're doing it a little differently, but that'll work.
Oh.
You can see the same thing. Just-
You called R2 Z2?
Yeah.
Okay, that's fine. That also works. You can do that as well. You have Z3 and Z2.
And since they're just resistors, we can simply move straight to adding them. So what I did is I added Z3 to the inverse sum of Z2 inverse plus C1 inverse. And that's what I did for my Z total.
Oops, sorry, that is Z1. Did anybody do it differently?
happens.
So if you guys all did this, what should Z2 be?
Q2 should be 22 ohms plus 0.
Okay. And that would mean Z3 would have a similar looking equation, so 56 ohms plus 0J. So I'm gonna rewrite some of this on the next slide. I know the circuit's still there. We'll rebox some stuff. So our goal for ZT is gonna be Z3 plus 1 over Z2 plus 1 over Z1 inverse, where now I have Z1 is, that is our 33 plus, the case we're running, it's 20 pi. I'm just going to write that down here. I have Z2, which is 22 plus J0, and I have Z3 here, which is going to be 56 plus J0. So these are all of their rectangular forms for going through and doing that. And again, to remind ourselves, this mess over here is Z1, this is Z2, and this is Z3. So looking at it here with Z1 and Z2, and let's do Z3 as well. Let's just talk about them all at once. Do I need to convert any of them into polar?
No.
Why not?
When you do the parallel part, it will put it back to where it won't be a division anymore. So you wouldn't necessarily need the polar form. You could put in polar, but I feel like it'd be more difficult due to it just being all addition.
You guys agree?
No,
Okay. Why not? Okay, not to agree.
would you have to? 1 over?
No, because when you're doing the 1 over, it'd be 1 over the rectangular form plus 1 over the other rectangular form. When you add the two together, flip it over, it would fix, right?
That's what we're figuring out.
And I mean, we just take,
Oh, no, I don't know. Just, it wouldn't, maybe I should have said yes.
I don't know.
if we hypothetically believe that somehow two inverses don't make it right, even then, it doesn't mean our complex number is an issue. Like, since it's a unique term being added, it's just like adding polynomials.
We split them in half. We
What do you mean split them in half?
do just the resistance for half of it and then do just the.
That we cannot do. That we're gonna put a hard stop to right now.
If you just plug it into up top, can I get the answer?
But allow me to write it out first before you give an answer.
Five plus 12x to 37, you get 32 plus 12x. If you have 5 plus 12x, one quantity, and then you add another quantity, which is 37, then you get 42 plus 12x. Yeah. And let's say,
How do you add it when they're,
You'd have to get a common.
So I dropped the,
you have to make there be,
zeros.
yeah, how do you add them?
you can make them common. If you want to, but if you do them to make them common, you'll have a division that you need to have in polar.
You just do the result of this, you get 69.2, 62.832 rounded or 25.
Well, yeah, but how do you add 1 over 22?
You can separate it out because of a real division. So 1/33 plus J20.
Are you gonna be upset when I tell you that the numbers you just said are wrong?
Are they?
Yeah,
How do you,
So 40.
how do you do that?
there's not, there's no 47s.
I'm at 74.
I didn't say 40.
I said 70.
He just said 47. Can you repeat your numbers?
69.2 plus J 62.832.
I think
That is not correct.
and neither is
Wait, wait,
74.
wait, say what you said.
74.2 is correct.
Is correct?
Yes.
I figured it out.
What'd you get for your imaginary term?
4.36. Oh,
That one didn't work out. That might be a rounding thing though. All right, so. I don't know. I know Tristan here looked at it. I don't know if anybody else looked at it. But if you go to chapter 15, right, it's got the stuff about the complex number system. There's this really cool portion of the textbook, an example 15.4, that tells you how to do all this in your calculator. If you would like to learn how to do it that way, that's fine with me. You do have to have a graphing calculator do it, but it does the math for you. Because again, typically you're not going to be hand doing this math.
15, what?
Example 15.4. So I did it in polar. You are welcome to do it in polar. That is fine.
This is right.
This is rectangular.
That makes sense.
So if we look at it in polar, nothing, the only part that would need to be in polar is the part in the parentheses. So the fun thing is nothing changes with the resistor value, that because we don't have the imaginary part, so it's 0 degrees. We'll put it in here to indicate it, but it's a 0 degrees plus. So for Z1 in polar, it's 70.907. And the angle is 62.291 degrees. So this is the polar version of it. To go from rectangular to polar, you square both terms, add them together to get the magnitude, and then for the angle part, or sorry, you don't do that. Right, because these are, they're in series. So Z1 is equal to the square root of R3 squared plus XL squared. And the inverse tangent, theta is equal to the inverse tangent of XL over R3. So this is, again, because Z1, they are in series. There's no imaginary part. So for this here, right,
No, you see.
Z1 is just R, or Z2 would just be R2 squared.
Oh,
And
that's
then
not combined
you
together.
have 0.
No, that's imaginary.
So, but there should be, you can have this.
Yeah, it's just,
They are.
it's just
they're
we also
imaginary.
make 0.
Oh, you did your calculation.
Yeah.
That would be
Section of it all by itself. Combined.
33 squared plus.
Why would that give us a different number?
Square root.
And that's the 70.9707. Mhm. Yep. So theory, both forms, depending on your confidence level, should get you to the same answer. Sorry, this should have a -1 here. Once we have this part done, then we need to add it rectangular wise to the 56. We'll do this. So again, you don't have to do it a specific way, just you need to be careful with the way that you are going through and doing it.
So then with this, you would add it, if it's 1/22 plus 1/70. And then I'll give you an equal.
So when you would go through and do this, you flip it all over. So you should have, yeah, you can use the conductance and stuff there, and then add them together as rectangular.
You multiply them against each other, so you get the same common denominator.
If you want to keep it like this, yeah, you cross multiply, do your stuff that way. Or you can go through and put it in terms of G and BL. Which, right, those are the inverse. Put them in polar, add them together, and do it that way. So we can cross multiply. So give them the same denominator for going through and doing that. I don't have space here, so give me 1 sec to rewrite everything. So, oops. So we would have 70.9707 62.291. Oops. 291. You do your cross multiplication, and then you're able to add the two terms together. So you can add the two terms together. You'll have to do the addition again in rectangular. Then you can go through and do your division. And it takes a lot of little annoying math steps to do it. Which is why I'm okay if you learn how to do it in your calculator. Sorry. Inversed.
What section?
Hmm?
Sections.
That is example 15.4. So chapter 15, section 1 is where it goes through and introduces that. 15.4, and then a little bit further down in 15.1, it talks about the multiplication portion of it as well. And how to do that just directly in your calculator. So in theory, regardless of what method you go through and do, so if I just do this part here, so for Z2, or sorry, not Z2, for Z2 plus 1 over Z3 inversed, if we take it and plug it in, I had messed up my numbers, so I only wrote 3 sig figs at this point moving forward. I got 18.2 ohms plus J 4.24 ohms. So this is doing all the math, putting it into rectangular form. And then to do the final value, so for ZT, that's going to be Z3 plus 1 over Z2 plus 1 over, sorry, that should be Z1. Z1 inversed, so that will get me my 56 for Z3 plus 18.2 ohms plus J 4.24 ohms. So I only need, there's no other imaginary term, so I don't need to worry about changing those values. So I just need to add the two real parts. I get that ZT is equal to 74.2 ohms plus J 4.24 ohms. How did I do this? By hand, not on this piece of paper, and very, very just wrote numbers down. So I didn't work it out.
Something
Please. So I added the top parts together, just had the one denominator.
Don't to add, you have to be in
I
rectangle.
I did, I just did it in a separate step. I put it together into one thing first. Also, I realized that number's wrong. Let me fix that. So it's oops. So I put it all together to make my brain happy. I went through, I multiplied the 22 to the 70 part, when I did that. And then in my top, I had, cause I already have this in polar form,
But to add,
or I already have it in rectangular as well, right? That's how I originally had it. So I added this to it. So you have 55 and the stuff, and then you go through.
over.
Yeah.
What'd you numbers?
In polar, and then you just flip it over unless the sign of the angle flips. But it's 1 over whatever it is, and you just flip the sign of your angle. Any questions about 29? There aren't any questions about 29. That's all I have. As a reminder, your exam is going to go live tomorrow at noon. Tomorrow being Friday. You'll have the 36 hours to do that. And yeah, you'll be good to go for that. So, if you have any questions while you take the exam, please be sure to ask.